Hello everyone, thank you for joining me today. Codility has a respectable challenge here in the GenomicRangeQuery lesson in their prefix sum section. To me, this is more than respectable. I'm not gonna lie, this was a very difficult task for me, and as you will see, I bombed it the first few times before I even got some kind of semblance of an efficient performance score. My goal is to keep this video at a decent length, so let's get to it and dive right in. We have a lot of ground to cover. What this problem is asking us to solve is very complicated, so I hope I can be clear and concise with all the information. I'm not going to go over Codility's explanation since you can read that for yourself. What I am going to do is give you my explanation. We have an array labeled S consisting of the letters A, C, G, T. The way Codility has this string threw me a little as they're not broken up into characters within the array. Because I failed the first time so badly, I figured it was part of the problem and decided to turn the array into a list of individual letters in my second solution. Still wrong. Anyway, I digress. When Codility says ranges, think of it as slices. We have our array of S here showing the indices. Then we have two queries labeled P and Q. Now that you see them like this, just for understanding's sake, take the label P and Q away just for a moment. We have 2 through 4, 5 through 5, and 0 through 6. These are the ranges, or the slices, of the array that we need to perform. Take a look here for the first slice of 2 and 4. We need to slice the array at the indices of 2 and 4. And within that slice, we have the letters G, C, C. Since those letters hold their own values, A equals 1, C equals 2, G equals 3, T equals 4, their values look like this in the array. The problem Codility is asking to solve is to return the minimal impact factor, or number value for the letter. For our first slice of 2 through 4 in the array, the lowest letter is C, producing the value 2. 2 is our minimal number, so it's the first answer in the solution. Our second slice is just one letter at index position 5, so we will just return a 4 in our second spot in the solution. Hopefully you will understand what's going on by our third slice, and this is making sense to you. Our third slice is the entire array from index position 0 through our last letter at position 6. Our minimal letter is A with a value of 1, so it will return a 1 in our last slot of the solution answer. So, how do we do this? To be sure, there are a lot of ways we can solve it. But if you know me by now, simple, simple, simple is my preference. Short and sweet. Many of the codes I studied were excruciatingly long and extremely hard to understand, so we aren't going to cover those. Although I did include one example of the longer code that I personally wouldn't use, I chose to show it here for demonstrative purposes. For my very first attempt, it did yield a correct result for the example Codility presents. However, it failed everything, giving me a 0%. That's kind of unfair since I did get a tiny portion of it right. Here was my thinking behind it. If I just append a new list yielding the values for the keys, then I can create variables for A, B, and C, then implementing the min function. By returning the min of each index, it does give a right answer, but it's incorrect for what Codility is asking for. Because my line of thinking had to do with the way the array of S was presented, as stated earlier, I tried splitting the letters into individual characters and then enumerating that result labeled X. I still used the min function, only this time I used the indices instead of the values. I got a better result at 12%, which meant I was closer, and although I still wasn't there, I knew I was onto something. After taking a break to do more studying, I wanted to hold on to the key, so to speak, no pun intended, on using the list append. I felt like it was the right way to go. It took me a long time to figure out that they were asking for a list slice, or a portion of the array, not just the min factor. Although they are asking for that, they are asking for the min of the range. Duh. This third example here keeps the min, but implements a start point and an end point by zipping P and Q together. Then it just returns a new list with only the min value for each loop through of the start point to the end point for the for loop. This example will produce 100% across the board. Our fourth example doesn't use the zip, but does use two for loops. One looping through only amount of times the length of p is. Side note, q will always be the same length of p because they are start and end points in the array. You can't have a start without an end, so they will always be evenly matched in length. In place of the zip function, this code uses the indices of p and q within s, and then appends the list very similar to the way it was done in our last example. This will also garner a 100% performance. The fifth example is the lengthy code I was talking about earlier. So much writing. I can't really explain why, but I saw 3 or 4 lengthy examples like this that attempt to produce counts of the occurrences that the genomic letters make in the array. As shown, there are 2 A's, 3 C's, 1 G, and 1 T. It makes a counter of zeros, and then after enumerating S, it creates a count input. Please don't ask me why. Maybe it's just way beyond me. So then in the second for loop, it again makes a start point and an end point, like our previous example, and then it loops through. I'll explain what it's doing. This is where it gets a little confusing. What it's doing is looping through looking for an A. Since our first range contains G, C, C, and there is no A, it goes back and loops through again. This time it finds a C, 2 of them in fact, and since C's value is 2, it appends the list and puts a 2 as the first input in the solution. The next loop through is at position 5 and 5, so it doesn't find an A, it goes back, doesn't find a C, it goes back, doesn't find a G, it goes back. Now it finds the T in the else statement, so it inputs the 4 in the solution. It's at this point for this range, it doesn't have to travel very far as the A is at the first position, right after the first index of 0. It just happens to be a coincidence that it's at the index of 1, but the code will append the list and add a 1 because A's value is 1 to our last spot in the solution. 100% performance. For our last example, you will see that the counting of the occurrences in the array is not necessary. In fact, it isn't even necessary to provide a dictionary of the values for each nucleotide. This by far is the easiest and most efficient solution, at least to me. I found myself so confused over the lengthy codes that I saw, and even though I couldn't exactly articulate as to exactly why they were bothering me, now I know. As shown in my first few attempts, I knew it had to be simpler than what most people were producing. In this last example, we're still making a new list and appending it by the length of P, which is 3, slicing it in accord with the indices of P and Q, plus 1 for Q because, well, it's Python, and then appending it the same way it was done in our last example. If there's an A, do this, else if there's a C, do that, so on and so forth. Since there are no G's in our slices, this nucleotide will always get skipped over. In the end, this solution brings a correct time complexity of O, N plus M and gives 100% in performance. Thank you for watching, and I hope this video was helpful to you. Daily videos throughout the week are coming out, so don't forget to subscribe.